exactly.
Exactly. We'll know if he watches it or not because he's supposed to work on school, not science Olympiad.
School, not science Olympiad.
I'd say something towards JoJo, but we know she's not gonna watch it.
On that note, 6.8, we're talking about the standard enthalpies of formation. So the difference here between what we've had so far, the F stands for formation, and then there's that degree bubble, the degree sign. That signifies the standard part. So it's defined as the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard states. So the degree symbol tells us that the thermodynamic function indicates the corresponding process has been carried out under standard conditions. And we'll talk about those in a second, what those standard conditions are. But a standard state is just a reference state. And we're going to get into later on entropy, which is the letter S instead of H, and Gibbs free energy, which is a G. And all of those could have this degree symbol, just meaning that they're at standard conditions. Okay. So for a compound, the standard state of a gaseous substance is at a pressure of exactly 1 atmosphere. For a pure substance in a condensed state, meaning liquid or solid, then the standard state would be the pure liquid or solid. And for a substance present in a solution, standard state for concentration would be 1 molar. Then for an element, the standard condition state of an element is the form in which it exists under the conditions of 1 atmosphere and 25 degrees Celsius. That is not STP, standard temperature and pressure, because standard temperature is 0, but standard state conditions for thermodynamics would be room temperature, which is the 25 degrees Celsius. So basically, whenever you see tabulated data, because all of this is going to be tables, you don't have to actually know the numbers, you just have to plug them into the equation. It will probably tell you collected at 1 atmosphere and 25 degrees Celsius. Just means that it's standard state. Okay. So this table I provided for you in your notes. It is in your textbook. Write this down because you're going to need this for the homework problems. More values than just these. These work for example, but they don't work for everything. More values are found on A19 in the textbook. So if you can't find it here, then A19 has loads and loads and loads of different things for you to find. So for those who listen who watch without audio on the video, more on page A19. Okay, so now you never include elements that are in their normal state at these standard conditions. They will never have a number. So if you can't find it on the number or you can't find it on the table, that means that the standard change in formation is just 0 kilojoules per mole. And that would be elements, that could be diatomic molecules. It's just anything that would be by itself or diatomic at natural state. So like not like ammonia, but if it was just like nitrogen gas, that would be a 0. Okay, so and if it's a 0, you just don't include it in the equation. It makes life simpler. The enthalpy change for a given reaction can be calculated very similarly to 6.7, but the difference is now we are taking the products minus reactants. And that's backwards from 6.7. So the standard enthalpy change for the reaction is going to be products minus reactants. And that's because it's for the formation, not for the breaking, which 6.7 is all about the breaking of bonds, and 6.8 is all about forming bonds. Okay, so that's why it's the difference. You still want to take the sum of all the reactants and the sum of all the products, and you still want to multiply by the moles of each reactant or product. This time, though, we do not have to count the individual bonds. We'll just use, to find the ends, we'll just use the coefficients from the equation. So you don't necessarily have to draw the actual Lewis structure this time. The Lewis structure was important before because it was about each individual bond. but now it's about just the overall compound. So just the coefficient in front of it is all that you need to multiply by. Okay, so we have example 10, and then that's it. Why isn't it going forward? Okay. So using standard enthalpies of formation listed in table 6.2, which is on page 5 of your note packet, calculate the standard enthalpy change for the overall reaction that occurs when ammonia is burned in air to form nitrogen dioxide and water. Okay, so before anything else, what I like to do with these is I like to make sure that I get the numbers in the right spots. So looking back on page 5, what is the value for NH3? Negative 46? Okay. And then, do you find O2 anywhere there? No. That one's going to be a 0. So this is a case that, at standard conditions, oxygen gas has already been formed. That is its state of matter that it likes to be at. So it just has a value of 0. Okay? Then NO2, 34, and H2O, negative 286. Okay. So let's, before we even do the final, let's just do the reactants and products to get those numbers, and then we'll subtract. So you take the coefficient times the value, so we have 4 times negative 46 plus 7 times 0 for the left, and then 4 times 34 plus 6 times negative 286 for the products. So do you want to just tell me what one of the two sides are?
Negative 184.
For the reactants?
Yes.
Okay.
The other side's
I got -60. I got that.
it's 1,852. Well,
I got
oh wait, never
1,000.
mind, never mind. I take it back, I take it
Oh,
back, I take
wait.
it back. I've added this, right?
Yeah, that's right.
Yes.
I was going off just the 6 times the
Oh.
286.
Okay. Okay. So then now for the standard enthalpy of formation, what we're solving for the reaction, we need to take products minus reactants. So we'll have negative 1580 minus a negative 184. Negative 1396? Okay, and remember, since we are subtracting or adding, we just keep the same number of decimal places, so that we would just keep it as negative 1396 for the answer. And then the unit would be kilojoules, because the per mole from all the values in the table has been canceled out by multiplying by the coefficients. That's technically the moles of it. So that's that. That's all. If you ever accidentally put per mole, it'll probably be fine.